The comet appears first as a smudge of light against distant stars, unremarkable to most eyes. It moves through the plane of the solar system at an angle that feels wrong, too steep, too fast. Its trajectory does not match the rhythms of objects born here. The numbers tell astronomers what eyes cannot. This visitor formed somewhere else, in orbit around another star, and spent perhaps millions of years drifting through the space between suns before arriving here. Now, in the inner solar system where Earth's telescopes can see it, they name it 3I/Atlas. The designation means it is the third confirmed interstellar object detected passing through, following 1I/Oumuamua in 2017 and 2I/Borisov in 2019. Atlas refers to the survey system that found it, a network of robotic telescopes in Hawaii scanning the sky each night for anything that moves or changes. The comet does not know its name. It tumbles silently, shedding water vapor and dust as sunlight touches ice that has not felt warmth in epochs. What captures attention is not the comet's brightness or size, but something quieter: its spin. All objects in space rotate. Asteroids, planets, moons, comets, they all carry angular momentum from their formation, from collisions, from the slow grind of gravity and time. But this comet's rotation is changing, not quickly, not dramatically, just tilting. The axis around which it spins shifts by fractions of a degree over weeks, a wobble so subtle that only precise measurements reveal it, and in that wobble lies a story. The comet itself is small, perhaps a few hundred meters across, though exact size remains uncertain. Its nucleus, the solid core of rock and ice, reflects very little light. Most of what astronomers see is the coma, the cloud of gas and dust surrounding the nucleus as ice sublimates in the sun's heat. The coma glows faintly, fed by jets erupting from the surface wherever sunlight strikes frozen volatiles. These jets are not symmetric. They do not spray evenly in all directions. Some parts of the nucleus outgas more vigorously than others, perhaps because the ice there is purer, or closer to the surface, or oriented toward the sun at the right angle. Each jet carries momentum. As gas molecules rush away from the surface at hundreds of meters per second, they push back against the nucleus itself, Newton's third law operating in the vacuum of space. These pushes are tiny but persistent. Over days and weeks, they accumulate. The comet's spin responds, slowly, like a top on a table nudged by invisible fingers. The spin axis tilts, the rotation rate changes. And astronomers, watching brightness curves flicker across their screens, begin to understand that this visitor is not simply passing through. It is speaking. What the comet says is encoded in light. As it rotates, different parts of the nucleus and coma reflect sunlight toward Earth. The brightness changes in a regular pattern, rising, falling, rising again, each cycle corresponding to one full rotation. By measuring these brightness variations over many nights, astronomers can determine the rotation period, how long it takes the comet to spin once around its axis. For 3I/Atlas, that period is roughly 7 hours, though it varies slightly as the outgassing torque acts on the nucleus. But the brightness curve does more than reveal rotation speed. Its shape, the exact pattern of peaks and valleys, tells observers about the comet's shape and orientation. A perfectly spherical comet would show no brightness variation at all. It would look the same from every angle. An elongated comet, shaped like a potato or a rugby ball, would brighten and dim twice per rotation as its long axis and short axis alternately face Earth. And a comet with an asymmetric surface, with bright patches and dark patches distributed unevenly, would produce a more complex curve, a fingerprint of its geology. 3I/Atlas shows complexity. Its brightness curve is not a simple sine wave, but something more irregular, suggesting that the nucleus is neither round nor uniformly reflective. Perhaps one hemisphere is darker, covered in a layer of organic tars left behind as ice sublimates. Perhaps the other hemisphere is fresher, still bright with exposed water ice. Or perhaps the shape itself is deeply irregular, a fragment from a larger body that broke apart long ago in some distant collision. The tilt in the spin axis adds another layer. If the comet were rotating around a fixed axis, the brightness curve would remain constant night after night, repeating precisely. But the curve changes. The timing of peaks shifts slightly. The amplitude varies. These changes are signatures of precession, the slow wobbling of the spin axis, like a spinning top that leans and circles as it slows. For 3I/Atlas, the precession is driven not by internal friction or gravity, but by external forces, the uneven push of outgassing jets acting on an asymmetric body. This is not unusual for comets, solar system comets, those born in the Kuiper belt or Oort cloud. In orbit around the Sun for billions of years, often show spin changes as they approach perihelion and outgassing intensifies. What makes 3I/Atlas remarkable is that it is interstellar. It's ice formed in a molecular cloud around another star, compressed by shock waves from supernovae, frozen at temperatures near absolute zero. It accreted into a comet nucleus in a protoplanetary disk that may have looked nothing like the young solar system. And then, somehow, it was ejected, flung out of its home system by gravitational interactions with planets or passing stars, sent drifting into the galaxy. For millions of years, perhaps tens of millions, the comet travelled through interstellar space. No sunlight touched it, no warmth. The ice remained pristine, undisturbed, a fossil of its birth environment. The rotation it carried from formation continued unchanged, conserved across light years, and then, by chance, pure, random chance, the comet's trajectory intersected the solar system's path through the galaxy. Gravity bent its course inward, sunlight found it, and ice that had been frozen since another star's youth began to sublime. Only took a few million years to get here, only needed to cross 4 light years of emptiness without hitting anything, only had to arrive at exactly the right angle to pass close enough for Earth's telescopes to notice. The probabilities are almost laughably small, and yet here it is, tumbling through the inner solar system, its spin axis tilting under forces it has never felt before. Astronomers watch. They measure. They calculate. The data accumulates: brightness curves, spectra, astrometric positions tracking the comet's path across the sky. Each observation adds a small piece to the puzzle. The tilt in the spin is not random. It follows patterns, driven by physics that can be modelled, understood, predicted. And in those patterns lies information about the comet's structure, its composition, its history, about where it came from and what it has endured. The comet does not care about any of this. It simply moves, bound by gravity and momentum, shedding ice into the void as it has done for weeks now, as it will do for weeks more until the sun's warmth fades behind it and the long cold returns. Spin is memory. Every rotating object in the universe carries information about its past encoded in the speed and direction of its rotation. A figure skater pulling in their arms spins faster. A planet forming from a collapsing cloud inherits the cloud's original angular momentum. For comets, spin tells the story of birth, of accretion in a protoplanetary disk, of collisions that merge smaller bodies into larger ones, of the chaotic early days when gravity sorted dust and ice into worlds. 3I/Atlas rotates once every 7 hours, give or take. This is neither particularly fast nor particularly slow for a comet. Some small bodies spin in minutes, tumbling wildly, their rotation accelerated by impacts or outgassing torques over billions of years. Others rotate once per day or slower, their angular momentum damped by tidal forces or by the gradual loss of mass. 7 hours suggests a body that formed without extreme violence, that accreted relatively gently, grain by grain, in a disk where collisions were frequent but not catastrophic. The direction of the spin axis matters too. In the solar system, most objects rotate in roughly the same plane and direction. a legacy of the disk from which they formed. The sun rotates, the planets orbit and rotate, nearly all in the same direction. Even the small bodies, asteroids, comets, Kuiper belt objects, tend to follow this pattern. Their orbits and spins aligned with the system's overall angular momentum. But 3I/Atlas does not belong to this system. Its orbit is hyperbolic, open-ended, a trajectory that entered from interstellar space and will exit to interstellar space again. Its spin axis points in a direction unrelated to the solar system's geometry. This is one of the first clues that it truly is interstellar, not just an unusual comet from the Oort cloud, nudged onto a strange orbit by a passing star, but an object born elsewhere, carrying the angular momentum imparted by a different star's protoplanetary disk. The angle is wrong. The speed is wrong. Everything about its motion speaks of origins light years away. Astronomers can estimate how long the comet has been rotating at this rate. If outgassing has been changing the spin significantly, and if the current 7-hour period is different from what it was before entering the inner solar system, then working backward through the torque models might reveal the original rotation rate, the spin the comet had when it was still far from the sun, dormant and frozen. But this requires assumptions. How strong are the jets? How massive is the nucleus? How much ice has sublimated? The uncertainties stack up quickly. What is certain is that the comet has been spinning for a very long time. Millions of years, at least. Possibly much longer. If it was ejected from its home system 10 million years ago, then it has rotated through roughly 12 trillion cycles in the darkness between stars. Each 7-hour spin identical to the last, undisturbed. A clock ticking in the void with no one to observe it. The thought is almost absurd. A tiny iceberg tumbling through space, rotating for epochs, carrying information about a stellar system that may no longer exist, arriving here by accident. The molecular cloud where the comet formed is gone now, dispersed by stellar winds and supernovae. The protoplanetary disk where it accreted, gone. Either incorporated into planets or blown away by radiation. The star itself may still shine, somewhere in the galaxy, perhaps with planets orbiting it, perhaps not. There is no way to know. The comet's trajectory, traced backward, points toward a region of sky several light years away. But the uncertainty is enormous. Interstellar space is vast. Stars move. The comet could have come from any of dozens of stellar systems that happened to be in that general direction millions of years ago. Still, the spin holds clues. The rotation period can be compared to models of comet formation. In simulations, small bodies accreting in protoplanetary disks tend to spin at rates determined by the balance between gravitational collapse and angular momentum conservation. If the comet formed from a slow, gentle merger of smaller objects, its spin would be relatively slow. If it formed in a more turbulent environment, or if it was the fragment of a larger body shattered by collision, the spin might be faster, more chaotic. 7 hours fits the gentler scenario, but not uniquely. Many formation pathways could produce this result. The tilt, though, the precession, the slow wobble of the spin axis, adds information. Precession happens when torques act on a rotating body whose mass is not evenly distributed. If the comet were a perfect sphere with uniform density, no amount of outgassing would cause the spin axis to tilt. The jets would push evenly in all directions, changing the rotation rate perhaps, but not the axis direction. But real comets are not perfect spheres. They are lumpy, irregular, with masses concentrated in some areas and voids in others. When jets erupt from an asymmetric surface, the torque they generate has a component that acts perpendicular to the spin axis, causing it to wobble. By measuring the rate of precession, how fast the spin axis tilts, astronomers can infer the comet's shape and internal structure. A highly elongated nucleus would precess differently than a nearly spherical one. A nucleus with a large, dense core and a fluffy outer layer would respond to torques differently than a uniform icy body. The math is complex, involving tensor moments of inertia and non-gravitational force models. But the principle is simple. Shape affects spin, and spin reveals shape for 3I/Atlas. The precession rate suggests an elongated body, perhaps twice as long as it is wide, with mass distributed unevenly along its length. This is consistent with what is seen in many solar system comets: irregular, potato-shaped nuclei sculpted by sublimation and impacts over billions of years. But whether this shape is original, dating back to the comet's formation, or whether it has been modified by processes during its long journey through interstellar space, remains unknown. Perhaps impacts with interstellar dust grains, though rare, have slowly eroded the surface. Perhaps cosmic rays have altered the ice chemistry, making some regions more volatile than others. Perhaps the comet is a fragment, broken off from a larger parent body in some ancient collision. There is also the question of composition. Spin alone does not reveal what the comet is made of, but it provides constraints. A nucleus composed mostly of water ice would have a certain density, around 500 to 1,000 kilograms per cubic meter, less dense than water because the ice is mixed with voids and dust. A nucleus with more rock and less ice would be denser, 1,500 to 2,000 kilograms per cubic meter. Density affects how the nucleus responds to torques. A low-density, fluffy comet would change its spin more easily under the same outgassing forces than a high-density, compacted one. Observations of the comet's brightness and the strength of its coma suggest a composition similar to solar system comets, mostly water ice, with smaller amounts of carbon monoxide, carbon dioxide, ammonia, and methane, mixed with silicate dust and organic compounds. This is reassuring in a way. Despite coming from another star system, despite forming in a molecular cloud with potentially different chemistry, the comet looks familiar. Water is water. Ice is ice. The universe, it seems, builds comets in similar ways regardless of where they form, but subtle differences exist. Spectroscopic observations, breaking the comet's light into its component wavelengths, reveal the presence of certain molecules in slightly unusual ratios. The carbon monoxide to water ratio is a bit higher than typical for solar system comets. The dust appears slightly redder, perhaps indicating a higher concentration of organic tars. These differences are small, within the range of variation seen among local comets, but they are real. They hint at formation conditions that were not quite the same as those in the solar nebula 4.5 billion years ago. Only took a few measurements to notice. Only needed a few nights of telescope time to see that something was slightly off. Only required comparing spectra to a database of known comets to realize this visitor carries chemistry from another system, another time, another part of the galaxy's history, and yet it spins here, in our sunlight, shedding ice that glows and sublimates just like any other comet, as if distance means nothing, as if all ice remembers the same cold. The comet continues its rotation. 7 hours, again and again. The axis tilts a fraction of a degree more. Brightness curves shift. Data accumulates. Somewhere in the pattern is an answer, a truth about where this body came from and what its spin can tell us about the disk where it was born. But truth comes slowly, pieced together from photons that travelled millions of kilometres to reach Earth's telescopes, interpreted through models and mathematics. Always uncertain, always provisional. The comet does not wait for understanding, it simply spins. The tilt reveals itself gradually, not in a single observation but across weeks of patient watching. On the first night that Atlas detects the comet, astronomers measure its brightness and note the variation, a gentle rise and fall over hours, suggesting rotation. On the second night, the pattern repeats, but the timing is slightly different. The peak brightness occurs a few minutes earlier or later than predicted. This could be measurement error, atmospheric distortion, the limitations of telescopes peering through Earth's turbulent air. Or it could be real. By the third night, the pattern is clearer. The brightness curve has shifted. Not dramatically, no sudden flips or chaotic tumbling, but enough to suggest that something about the comet's orientation is changing. Astronomers run the numbers through software designed to model rotating bodies, searching for an explanation. A fixed spin axis would produce a repeating curve, identical night after night, predictable as clockwork. This curve is not repeating, it evolves. The peaks drift, the shape warps subtly, the explanation arrives through mathematics. The comet is precessing its spin axis. Instead of pointing in a fixed direction relative to the stars, is slowly sweeping out a cone, like the wobble of a top losing stability. The precession period, the time it takes for the axis to complete one full wobble cycle, is estimated at several weeks, though the exact value remains uncertain. Measuring precession requires many nights of data, and the comet is moving, brightening as it approaches the sun, complicating the analysis, but the signature is there, unmistakable once recognised. Precession is common in rotating bodies subjected to external torques. Earth itself precesses, its axis tracing a slow circle in the sky with a period of about 26,000 years, driven by the gravitational pull of the sun and moon on its equatorial bulge. For comets, the torques come not from gravity but from outgassing, jets of gas and dust erupting from the surface as ice sublimates. These jets do not push uniformly, they are localized, erupting from specific active regions where sunlight strikes volatile rich ice. And because the nucleus is irregularly shaped, the jets create torques that act to change the spin axis direction. The fact that 3I/Atlas is precessing tells astronomers that its nucleus is not symmetric. If the comet were a perfect sphere, or even a uniformly dense ellipsoid, the outgassing torques would still affect its rotation rate, speeding it up or slowing it down, but would not cause the axis to tilt. The tilt requires asymmetry. The nucleus must be lumpy, with active regions located away from the spin axis, so that the jets push at an angle. Or the mass distribution must be uneven, with denser material on one side causing the centre of mass to be offset from the geometric centre. This asymmetry could be primordial, dating back to the comet's formation. Small bodies accreting in protoplanetary disks rarely form as perfect spheres. They grow through collisions, sticking together grain by grain, pebble by pebble, each impact adding mass in a random direction. The final shape depends on the history of impacts, whether they were gentle or violent, whether they added mass symmetrically or lopsidedly. A comet that accreted slowly, over millions of years, might grow into a relatively round shape as gravity smoothed out irregularities. A comet formed in a single catastrophic collision, as a fragment of a larger shattered body, would retain the jagged, irregular shape of the breakup, or the asymmetry could be evolutionary, carved by processes that occurred after formation. Comets sublime. Every time they pass close to a star, ice evaporates from the sunlit side, carrying away dust and leaving behind a dark, insulating crust. Over many orbits, this process sculpts the surface, creating cliffs and pits and active regions where fresh ice remains exposed. The comet becomes increasingly irregular, its shape determined not by how it formed, but by how it has sublimated. Solar system comets show this clearly, nuclei scarred by sublimation, with smooth plains next to rough highlands, with jets erupting from isolated pockets of ice surrounded by barren crust. For 3I/Atlas, the question is which process dominates. Is the asymmetry it shows today the asymmetry it was born with, preserved across millions of years in the cold of interstellar space? Or has the current passed through the solar system already begun to reshape it, creating new active regions, eroding old ones, sculpting the surface in real time? The precession rate provides a clue, but not a definitive answer. Models can fit the data with various combinations of shape, density, and outgassing distribution. Each model is plausible, none is proven. What is certain is that the tilt is small. The spin axis is not wildly unstable, not flipping chaotically from one orientation to another. The precession is gentle, almost imperceptible without careful measurement. This suggests that the torques acting on the nucleus are relatively weak, or that the nucleus is massive enough to resist rapid changes, or both. A small, fluffy comet subjected to strong outgassing would tumble more violently. A large, dense comet would resist torques more effectively. 3I/Atlas appears to fall somewhere in between, neither tiny nor enormous, neither completely stable nor chaotically spinning. The tilt also evolves as the comet approaches the Sun. Outgassing intensifies. More ice sublimates per hour. More gas rushes away from the surface. More momentum is transferred. The torques grow stronger. The precession rate might increase, or the axis might shift to a new orientation. Predicting this requires understanding the distribution of active regions on the surface, where the ice is, where the crust is thick or thin, how sunlight illuminates different parts of the nucleus as it rotates. Astronomers build models, input parameters, run simulations. The models predict a range of possible behaviours. Observations will eventually confirm or refute them, but that confirmation takes time. Meanwhile, the comet continues its slow wobble. The axis tilts another fraction of a degree. Brightness curves shift again. Somewhere in those curves is information about the nucleus's shape, encoded in the way light reflects off its irregular surface as it rotates and precesses. Extracting that information is painstaking work, comparing observed curves to synthetic curves generated by shape models, adjusting the models until they match, checking for self-consistency across multiple nights. It is detective work done with photons and calculus, piecing together a three-dimensional shape from a time series of brightness measurements. The shape that emerges is tentative, fuzzy around the edges, but suggestive. The nucleus appears elongated, with a long axis perhaps twice the length of its short axis. It might be roughly ellipsoidal, or it might have more complex features, a bulge here, an indentation there. The resolution is too low to see details like craters or cliffs, but the overall form is clear enough. Not a sphere, not a perfect ellipsoid, but something in between, a lumpy potato tumbling through space, its spin axis slowly sweeping out a cone as jets push against its surface. Only took a dozen nights of observations to notice the wobble. Only needed brightness measurements precise to a few percent to see the pattern shifting. Only required the assumption that the comet is a rigid body, not a rubble pile about to fly apart, to interpret the precession as evidence of asymmetry. The assumptions are reasonable. Most comets are thought to be relatively solid, held together by ice acting as cement between dust grains, strong enough to withstand the stresses of rotation and outgassing. But assumptions can be wrong. Perhaps this comet is more fragile. Perhaps the tilt is not precession at all, but something else. Some more exotic behaviour that looks like precession when viewed from Earth. Uncertainty lingers, as it always does in astronomy. The data is never perfect. The models are never complete. Every measurement comes with error bars, every interpretation with caveats. And yet the tilt is real. The spin axis is changing. Something is happening to this visitor from interstellar space as it passes through the solar system's warmth. Something subtle and slow but measurable. Something that speaks to the physics of rotation and torque and the delicate balance between angular momentum and external forces. The comet does not know it is being watched, that telescopes on Earth are tracking its every wobble, that scientists are debating the meaning of its precession. It simply rotates and precesses and moves forward on its hyperbolic trajectory, shedding ice into the void, axis tilting a little more each day. Sunlight is the engine. Without it, the comet would remain dormant, a frozen lump drifting through space with no coma, no tail, no jets. But as 3I/Atlas approaches the Sun, crossing the orbit of Mars and then Earth, the warmth increases. Photons strike the surface, transferring energy to ice molecules locked in the crystalline lattice. The ice absorbs heat. Molecular bonds begin to vibrate. At some threshold temperature, different for each volatile compound, but generally between 100 and 200 Kelvin, the bonds break. The ice transitions directly from solid to gas, bypassing the liquid phase in the vacuum of space. This is sublimation. Water ice sublimates slowly, requiring more heat to break its strong hydrogen bonds. Carbon monoxide and carbon dioxide sublime more readily, at lower temperatures. From regions of the nucleus still far from the sun, methane and ammonia fall somewhere in between. The comet's surface becomes a patchwork of activity, with different volatiles sublimating from different locations depending on composition and temperature. The gas rushes outward, away from the surface, expanding into vacuum at speeds of hundreds of meters per second. Dust grains embedded in the ice are carried along, dragged by the escaping gas, forming the coma that glows faintly in reflected sunlight. Each molecule leaving the surface carries momentum. Before sublimation, the molecule was part of the nucleus, rotating with it. After sublimation, the molecule flies away in a straight line, its momentum no longer contributing to the nucleus's rotation. This is a transfer of angular momentum from the solid body to the gas. But the transfer is not symmetric. If ice sublimated uniformly from all parts of the surface, the momentum loss would average to zero. Gas leaving the morning side would be balanced by gas leaving the evening side. The nucleus would lose mass but not angular momentum. Real comets do not sublime uniformly. The sunlit side heats up, the night side remains cold. Active regions, places where ice is exposed or close to the surface, outgas more vigorously than inactive regions covered by thick dust crusts. The result is that most of the gas and dust erupts from a few localized areas, creating jets. These jets are visible in high-resolution images of solar system comets, bright plumes streaming away from specific points on the nucleus, sometimes multiple jets from different locations, each tracing a curved path as the nucleus rotates and the jet sweeps across space like a lighthouse beam. For 3I/Atlas, direct imaging of individual jets is not possible. The comet is too far away, too faint, its nucleus too small to resolve with current telescopes. What can be observed is the overall coma, the cloud of gas and dust surrounding the nucleus, and subtle asymmetries in that cloud. The coma is not perfectly symmetric, it is brighter on one side than the other, suggesting that most of the outgassing comes from a preferred direction. As the nucleus rotates, this bright region rotates with it, creating a brightness variation that combines the effects of the nucleus's shape and the distribution of active regions. The jets create forces. Each jet acts like a tiny rocket engine, pushing against the nucleus. If a jet erupts from a spot near the nucleus's equator, aligned with the spin axis, the force pushes directly along or against the rotation direction, speeding up or slowing down the spin but not changing the axis orientation. If the jet erupts from a spot away from the equator, or at an angle, the force has a component perpendicular to the spin axis. This creates a torque, a twisting force that tries to change the direction of the axis. Over time, as the nucleus rotates and jets repeatedly fire, the torque accumulates, causing the axis to precess. The strength of the torque depends on several factors: how much gas is escaping per second, how fast the gas is moving, where the jets are located on the surface, and the nucleus's mass and shape. Larger nuclei, with more mass, resist torques more effectively. They have more angular momentum to conserve. Smaller nuclei respond more quickly to the same forces. Highly elongated nuclei, with mass distributed far from the centre, have larger moments of inertia and precess differently than compact nuclei. Calculating the expected torque requires modelling the outgassing in detail. Astronomers use thermal models to predict how much ice sublimates from each part of the surface as it rotates through sunlight and shadow. They estimate the gas production rate, how many kilograms of water vapour and other volatiles escape per second. They assume a direction for each jet, often perpendicular to the local surface, though the actual direction can be more complex if the gas flows through cracks or vents beneath the crust. They calculate the momentum carried away by the gas and the corresponding reaction force on the nucleus. The models are uncertain. The nucleus's exact shape is not known. The distribution of ice and crust is not known. The gas production rate is estimated from the comet's brightness, but brightness depends on how much dust is mixed with the gas, and that depends on the surface properties, which are not known. Each unknown parameter introduces uncertainty into the calculated torque. The result is a range of possible precession rates, consistent with the observations but not uniquely determined by them. Still, the models constrain possibilities. If the precession is as fast as observed, the torques must be at least a certain strength, which implies a minimum gas production rate or a maximum nucleus mass. If the nucleus were much more massive than estimated, the observed precession would require impossibly strong outgassing. If the nucleus were much less massive, the precession would be much faster unless the outgassing were very weak. By comparing models to observations, astronomers narrow the range of plausible nucleus properties. What emerges is a picture of a comet producing somewhere between 10 and 100 kilograms of gas per second at its current distance from the Sun. This will increase as the comet approaches perihelion, its closest point to the Sun, and decrease as it recedes. The gas escapes primarily from a few active regions, creating jets that push against the nucleus at angles determined by the rotation and the location of those regions. The torques from these jets are strong enough to tilt the spin axis by a few degrees over the weeks of observation, causing the measured precession. The physics is straightforward, almost mundane. Gas escapes, momentum is conserved, the nucleus responds, and yet there is something quietly remarkable about the process. This comet, born in another star system, shaped by forces that operated billions of years ago and light years away, now finds itself subjected to forces it has likely never experienced before. For millions of years in interstellar space, it felt no sunlight, no warmth, no outgassing. Its spin was constant, unchanged and conserved across epochs. Now, for a brief period measured in months, it passes through a region of space where a star's light is strong enough to sublime ice. Its spin changes, its axis tilts. The comet is being reshaped, subtly but measurably, by an environment foreign to its history. Only took a few hundred watts of solar energy per square meter to start the process. Only needed the nucleus to warm by a few tens of degrees above its interstellar temperature to begin sublimating volatiles. Only required that the comet pass within a few astronomical units of the Sun, a coincidence of trajectory, a chance alignment in the vastness of the galaxy. If the comet had entered the solar system at a slightly different angle, or at a different speed, it might have passed through the outer regions only, too cold to sublime, remaining dormant and unobserved. Instead, it comes close enough to wake. The jets continue. Gas streams away. Dust glows in the coma. Torques act on the nucleus. Slow and persistent, the spin axis tilts a little more. Somewhere in the data, in the accumulating brightness curves and spectra, is a complete description of this process. Every kilogram of ice that sublimates, every newton of force that acts on the nucleus, every degree the axis shifts. But extracting that description requires time, patience, and many nights of observation. The comet does not wait. It moves forward, bound by gravity, spinning and precessing under forces too small to feel but large enough to measure, writing its story in light for anyone who cares to look. Measuring the unmeasurable begins with light. The comet is too far away for any telescope to resolve its nucleus as more than a single pixel, a point source indistinguishable from a star except for its motion against the background sky. Yet, from that single point, from the way its brightness changes over hours and nights, astronomers extract shape, spin, precession, structure, a complete physical description built from photons. The method is called light curve photometry. A telescope points at the comet and measures how much light reaches the detector over a fixed interval, typically a few minutes, then another measurement and another, building a time series, brightness as a function of time. If the nucleus were perfectly uniform and spherical, the brightness would not change. but the nucleus is irregular, with different parts reflecting different amounts of sunlight depending on their orientation. As the nucleus rotates, bright regions and dark regions alternately face Earth. The measured brightness rises and falls in a pattern that repeats with each rotation. The challenge is separating the nucleus's contribution from everything else. The coma also reflects light, often more light than the nucleus itself, because the coma is larger, spread over a greater area. Gas molecules in the coma absorb sunlight and re-emit it at specific wavelengths through fluorescence. Dust grains scatter sunlight in all directions. All of this light combines at the telescope, creating a signal that is part nucleus, part coma, with no easy way to distinguish them. Astronomers use filters, pieces of glass that allow only certain wavelengths to pass through. A red filter blocks blue light, isolating the red part of the spectrum. A blue filter does the opposite. By measuring brightness through different filters, they can separate scattered sunlight, which has the sun spectrum continuous across all wavelengths, from fluorescent emission, which appears only at specific wavelengths corresponding to molecular transitions. The nucleus reflects sunlight continuously. Gas molecules like CN, C2, and OH emit at specific wavelengths. By subtracting the fluorescent contribution, what remains is mostly reflected light from the nucleus and dust. Even this is not perfect. Dust also scatters sunlight continuously, and dust in the coma can be optically thick, meaning it blocks some of the light from the nucleus behind it. The measured brightness depends on how much dust is present, how it is distributed in the coma, whether it is concentrated near the nucleus or spread more diffusely. These factors change as outgassing varies, adding noise to the light curve that has nothing to do with the nucleus's rotation. To minimize this, astronomers observe the comet repeatedly over many nights, accumulating enough data that the noise averages out and the underlying periodic signal emerges. Statistical techniques, Fourier analysis, phase dispersion minimization, periodogram methods, search for repeating patterns in the data. A rotation period of 7 hours means the brightness should cycle about 3.4 times per day. Over 10 nights, that's 34 cycles. Over 20 nights, 68 cycles. The more cycles observed, the more precisely the period can be measured, but the period is not constant. As the spin axis precesses, the orientation of the nucleus relative to Earth changes. Different parts of the surface become visible or hidden. The light curve shape evolves, peaks shift in time, amplitudes change, secondary peaks appear or disappear. This evolution is itself information. By tracking how the light curve changes, astronomers can infer the precession rate and the orientation of the spin axis. The math becomes complex quickly. The nucleus is a three-dimensional object with an unknown shape rotating around an axis tilted at an unknown angle, precessing at an unknown rate, all while orbiting the Sun and being observed from Earth, which is also orbiting the Sun. The geometry changes continuously. The amount of reflected light depends on the angle between the Sun, the nucleus, and Earth. The phase angle. At low phase angles, Sun behind the observer, the nucleus appears brighter due to the opposition effect, where shadowing between surface features is minimized. At high phase angles, the brightness drops because more of the observed surface is in shadow. Modelling this requires software that can simulate arbitrary three-dimensional shapes, calculate illumination and shadowing for every point on the surface, integrate the reflected light over the visible hemisphere, and account for the changing geometry as the nucleus rotates, precesses, and orbits. The software takes as input a guess at the nucleus's shape, often starting with a simple ellipsoid. Its spin axis orientation, rotation period, and precession rate. It generates synthetic light curves, what a telescope would observe if the model were correct. These synthetic curves are compared to the real observations. The model parameters are adjusted to minimize the difference. The process iterates until the synthetic curves match the observations as closely as possible. The result is a best-fit model, a set of parameters that describe the nucleus's shape, spin, and orientation in a way consistent with the data. But the model is not unique. Many different shapes can produce similar light curves, especially when only a limited range of viewing geometries is available. A long, thin ellipsoid viewed end-on looks similar to a short, wide ellipsoid viewed edge-on. Without additional constraints, stereoscopic observations from widely separated locations, or radar measurements that directly probe the shape, the ambiguity persists. For 3I/Atlas, the light curve data spans only a few weeks so far, covering a limited portion of the precession cycle. The viewing geometry changes as both the comet and Earth move, but not enough to fully break the degeneracies in the shape models. The current best fit suggests an elongated nucleus, roughly 200 to 400 meters in its longest dimension, with an axis ratio of perhaps 2, 1, 1, twice as long as it is wide. But this could be refined, revised, or overturned as more data accumulates. What cannot be directly measured is the internal structure. Light curves reveal only the surface, how light reflects off it, how its shape projects onto the sky. Whether the nucleus is solid ice, a porous rubble pile, or layered like an onion remains hidden. Density provides a clue. A measurement of both mass and volume would yield density, which constrains composition. But measuring mass requires observing the comet's gravitational effect on something else, a spacecraft flying past, or a companion object orbiting it. Neither is available for 3I/Atlas. The mass is estimated indirectly, from the outgassing torques and the observed precession, but the uncertainty is large. The rotation period itself offers a constraint. If the nucleus was spinning too fast, centrifugal force would overcome the weak gravitational self-attraction and the surface material would fly apart. The maximum safe spin rate depends on density and shape. For a typical comet density of 500 kilograms per cubic meter and a size of a few hundred meters, the critical period is a few hours. 3I/Atlas rotates at 7 hours, well below this limit, suggesting it is structurally stable, not on the verge of breaking apart. Only took decades of studying solar system comets to develop these techniques. Only needed hundreds of light curves from dozens of objects to calibrate the models and understand the systematics. Only required the assumption that interstellar comets behave similarly to local ones, that the same physics applies regardless of origin. The assumption seems to hold. 3I/Atlas looks, in most respects, like a comet from the Kuiper belt or Oort cloud, irregular, rotating, precessing under outgassing torques. If no one had told you it came from another star system, you might not notice. But the details matter. The precession rate is slightly faster than expected for a typical comet at this distance from the Sun. The light curve amplitude, the ratio of maximum to minimum brightness, is somewhat larger, suggesting either a more elongated shape or a more extreme difference in reflectivity between bright and dark regions. These are subtle differences, within the range of variation among solar system comets, but they are there. They hint that 3I/Atlas may not be entirely typical, that its formation environment or evolutionary history left marks visible even now. The comet continues to rotate. The light curve continues to evolve. Telescopes around the world track it, weather permitting, adding data point by data point to the growing archive. Each night's observations refine the models slightly, shrink the error bars a little, push understanding incrementally forward. The comet does not care. It simply spins, reflects light, and moves on. The ice remembers. Locked within the comet's nucleus are molecules that formed not in the solar system, but in a molecular cloud around another star, perhaps 4 or 5 or 10 light years away, perhaps 100 million years ago or more. These molecules carry isotopic signatures, ratios of heavy to light atoms, that encode information about the conditions where they condensed from gas into solid grains, deuterium to hydrogen, carbon-13 to carbon-12, nitrogen-15 to nitrogen-14, oxygen 18 to oxygen 16. Each ratio is a fingerprint of temperature, pressure, radiation environment, the composition of the parent cloud. Water ice dominates the composition, as it does in most comets. H2O molecules, simple and abundant, the product of hydrogen and oxygen combining in cold, dense regions of interstellar space. But not all water is identical. A small fraction, perhaps one molecule in 6,000, contains deuterium instead of ordinary hydrogen. Deuterium is heavy hydrogen with a neutron added to the nucleus. It behaves chemically like hydrogen but forms slightly stronger bonds, making deuterium-enriched molecules slightly more stable at low temperatures. The deuterium to hydrogen ratio in water ice depends on where and how the ice formed. In very cold environments, molecular clouds at 10 or 20 Kelvin, deuterium becomes enriched in molecules because deuterium-containing species condense onto dust grains more readily than normal hydrogen species. In warmer environments, the enrichment is less. By measuring the DH ratio in cometary ice, astronomers can infer the temperature of the environment where that ice originally formed, and compare it to the DH ratio in solar system objects to see if the formation conditions were similar or different. For 3I/Atlas, spectroscopic observations attempt to measure this ratio. The challenge is detecting the faint signal of deuterium. Water vapor in the coma emits light through fluorescence. Molecules absorb sunlight and re-emit it at specific wavelengths characteristic of the molecular structure. Normal H2O emits at certain wavelengths. HDO, water with one deuterium atom, emits at slightly different wavelengths because the heavier deuterium atom changes the vibrational frequencies. The two signals are separated by only a fraction of a nanometer. Distinguishing them requires high spectral resolution and large telescopes to collect enough light. Early observations suggest a DH ratio similar to that seen in many solar system comets, around 0.0003 to 0.0005, or roughly 2 to 3 times the ratio found in Earth's oceans. This similarity is intriguing. It suggests that the molecular cloud where 3Y/Atlas formed had temperatures and conditions not dramatically different from the solar nebula. Water ice condensed in similar ways, at similar temperatures, from gas with similar isotopic composition. The galaxy, it seems, is more uniform than one might expect. Star formation proceeds along similar pathways, producing similar distributions of ice and dust, regardless of location. But there are differences. The carbon monoxide to water ratio is elevated, more CO relative to H2O than typical for Jupiter family comets, which originate in the Kuiper belt. This could mean the comet formed in a colder region of its protoplanetary disk, farther from its host star, where CO ice could condense without sublimating. Or it could mean the host star was cooler than the Sun, shifting the snow lines, the distances from the star where different volatiles freeze, inward. A red dwarf star, smaller and dimmer than the Sun, would have snow lines much closer in, with CO ice forming in regions that, around the Sun, would be too warm. The organic content also differs subtly. Spectroscopic observations detect cyanogen, Cn, diatomic carbon, C2, and hydroxyl, OH in the coma, typical cometary species, produced by the breakdown of parent molecules like HCN, C2H2, and H2O under ultraviolet radiation. But the ratios between these species are slightly unusual. The Cn to OH ratio is higher than average, suggesting that the comet is richer in carbon and nitrogen-bearing organics relative to water. This could be primordial, reflecting the composition of the molecular cloud, or it could be evolutionary, the result of preferential loss of water ice over multiple passages near a star in its home system before ejection. The dust in the coma also tells a story. Dust grains reflect sunlight, and the way they reflect, how much light at different wavelengths, how the brightness changes with phase angle, reveals the grain's size, composition, and structure. For 3I/Atlas, the dust appears redder than typical solar system comets. meaning it reflects more light at longer, redder wavelengths than at shorter, bluer wavelengths. This reddening could be due to organic tars coating the grains, complex carbon molecules produced by radiation processing of simpler ices over millions of years in interstellar space. These organic tars are sometimes called tholins, a term coined to describe the reddish-brown material created when ices like methane, ammonia, and nitrogen are exposed to ultraviolet light or energetic particles. Tholins form in cold environments where ice is abundant and radiation is present, exactly the conditions in interstellar space. Cosmic rays, high-energy particles streaming through the galaxy, strike the comet's surface and penetrate into the ice, breaking molecular bonds and creating reactive fragments that recombine into more complex structures. Over millions of years, a layer of tholin builds up, darkening and reddening the surface. If 3I/Atlas spent millions of years in interstellar space, exposed to cosmic rays with no star nearby to sublime the ice and refresh the surface, then it should have accumulated a significant tholin layer. The observed reddening is consistent with this idea, though not proof. Solar system comets also show varying degrees of reddening, likely due to similar radiation processing in the outer solar system, so the presence of red dust alone does not uniquely indicate interstellar origin, but combined with the elevated COH2O ratio and the unusual CNOH ratio, a picture emerges of a comet that has experienced a history different from most local comets. The isotopic ratios of other elements could provide more definitive answers. Nitrogen isotopes, for example, vary widely among solar system objects depending on formation location and subsequent processing. Measuring the 15N-14N ratio in ammonia, NH3, or hydrogen cyanide, HCN, from the comet would reveal whether the nitrogen came from the same reservoir as solar system nitrogen or from a different source. Similarly, sulfur isotopes, oxygen isotopes in CO or CO2, and noble gas abundances, helium, neon, argon, all carry information about the comet's origin, but these measurements are difficult. Many of the relevant species are faint or emit at wavelengths that are absorbed by Earth's atmosphere, requiring space-based telescopes or high-altitude observatories. The comet is relatively dim, producing only small amounts of gas, so the signals are weak. Extracting accurate isotopic ratios from weak signals is challenging, prone to systematic errors and contamination from other sources. The data exists but remains preliminary, subject to revision as more observations accumulate and analysis techniques improve. What is clear is that the comet is not made of exotic matter. No unusual elements, no materials unknown in the solar system, water, carbon monoxide, carbon dioxide, silicate dust, organic compounds, all familiar, all explainable by standard chemistry and physics. If anything, the comet is reassuringly ordinary, despite travelling for millions of years across light years of space. Despite forming in a molecular cloud associated with a different star, it looks and behaves like objects that formed here. The universe, it seems, builds comets from the same ingredients everywhere. Only took billions of years for those ingredients to assemble. Only needed a molecular cloud to collapse, a star to ignite, a disk to form around it, dust and ice to stick together grain by grain. Only required that the resulting comet be ejected before it could crash into a planet or the star, that it survive the ejection without shattering, that it drift through interstellar space without colliding with anything, that it enter this solar system at the right angle and speed to be detected. The chain of improbable events stretches back across time and distance, each link necessary, each fragile. And yet here it is, sublimating in the sun's light, releasing molecules that remember another star. The comet does not reflect on its origins. It simply sublimates, releasing what it carries into the solar wind. One molecule at a time. Comparison is inevitable. Every measurement of 3I/Atlas is immediately weighed against the properties of solar system comets. the hundreds of objects catalogued and studied over decades. Orbiting the Sun in elliptical paths, returning periodically or arriving once from the distant Oort cloud, these local comets provide the baseline, the standard against which the interstellar visitor is judged, and in most respects 3I/Atlas fits comfortably within the range of variations seen among its local cousins. Solar system comets rotate with periods ranging from a few hours to several days. Most fall between 4 and 12 hours, with a median around 8 hours. 3I/Atlas, at 7 hours, sits near the middle of this distribution, not unusually fast, not unusually slow, just another tumbling ice ball, indistinguishable by rotation rate alone from a comet born in the Kuiper belt or the Oort cloud. Their shapes, too, vary widely, but within predictable bounds. Spacecraft that have visited comets, missions like Rosetta to 67P/Churyumov-Gerasimenko, Deep Impact to Tempel 1, Stardust to Wild 2, reveal nuclei that are lumpy, irregular, sometimes bilobed as if two objects had gently merged. The axis ratios range from nearly spherical to highly elongated, with most falling in the range of 1.51 to 2.51, the inferred shape of 3I/Atlas, elongated with an axis ratio around 2. 1 fits this pattern. It could easily be a solar system comet, based on shape alone. Albedo, the fraction of sunlight reflected rather than absorbed, provides another point of comparison. Cometary nuclei are among the darkest objects in the solar system, reflecting only 3 to 5% of incident light. Their surfaces are covered in dark, carbonaceous material, dust mixed with organic tars, baked by repeated exposure to sunlight, forming an insulating crust that retains heat and inhibits sublimation. 3I/Atlas appears similarly dark, with an estimated albedo around 4%, again, unremarkable. Again, consistent with local comets. Even the composition shows more similarity than difference. Water dominates, as it does in nearly all comets observed so far. Carbon monoxide, carbon dioxide, methane, ammonia, all present in proportions that overlap with the ranges seen in solar system comets. The elevated COH2O ratio noted earlier is unusual, but not unprecedented. Some Oort cloud comets also show high CO abundances, likely because they formed in colder regions of the solar nebula, or because they have experienced less processing by sunlight. The ratio places 3I/Atlas at one end of the distribution, but still within it. The dust-to-gas ratio, how much solid material is released relative to gas, is harder to measure but appears normal. For most comets, each kilogram of gas carries away a few hundred grams of dust, though the ratio varies depending on the comet's activity level and the size distribution of dust grains. Observations of 3I/Atlas's coma brightness and spectroscopic measurements of gas production suggest a dust-to-gas ratio around 0.5 to 1, typical for active comets. The dust grains themselves, reddish and organic-rich, resemble those seen in the comae of local comets. Where differences appear, they are subtle and often ambiguous. The precession rate is somewhat faster than expected for a comet of this size and activity level, suggesting either a more elongated shape or a different internal structure, perhaps less dense, more porous, with mass distributed differently. But the uncertainty in the measurements is large enough that this difference might not be real. More data could shift the estimated precession rate back into the normal range. The coma's asymmetry is slightly more pronounced than average, with a bright jet-like feature visible on one side. This could indicate particularly active regions on the nucleus, or it could simply be a matter of viewing geometry, Earth happening to be positioned to see the jets edge on rather than head on. Solar system comets show a wide variety of coma morphologies, from nearly symmetric spheres to highly asymmetric, with multiple jets and fans. 3I/Atlas falls somewhere in the middle, asymmetric, but not extraordinarily so. One property that might genuinely differ is the nucleus's mechanical strength. Solar system comets occasionally break apart, sometimes spontaneously, sometimes after close passes by the Sun or Jupiter. The breakup reveals something about their internal structure. They are not monolithic blocks of ice, but aggregates, loosely bound collections of smaller pieces held together by ice and self-gravity. If 3I/Atlas is more fragile, held together less tightly, it might break apart under stresses that a typical solar system comet would survive. But so far, it shows no signs of fragmentation. It remains intact, rotating stably, shedding ice without disruption. The spin evolution also offers clues. Some solar system comets show dramatic spin changes, rotation periods that increase or decrease by tens of % over a single apparition, spin axes that flip entirely, tumbling states that transition between stable rotation and chaotic wobbling. These changes are driven by outgassing torques acting on asymmetric nuclei, the same mechanism affecting 3Y/Atlas. But the magnitude of the changes depends on the nucleus's internal structure. A solid nucleus resists spin changes more effectively than a rubble pile. A dense nucleus is harder to torque than a fluffy one. For 3I/Atlas, the spin changes so far are modest, a precession of a few degrees, a rotation period that may have shifted by a few minutes but remains close to 7 hours. This suggests a nucleus that is relatively robust, able to resist the torques without dramatic reorganization. Or it could simply mean the comet has not yet experienced strong enough outgassing to drive larger changes. Perihelion is still ahead. As the comet gets closer to the Sun, activity will increase, torques will strengthen. What happens then, whether the spin remains stable or begins to change more rapidly, will reveal more about the nucleus's structure and strength. Comparing 3I/Atlas to the other interstellar objects detected so far, 1I/Oumuamua and 2I/Borisov, also provides perspective. Oumuamua showed no detectable coma or outgassing, leading to debate about whether it was a comet or an asteroid or something else entirely. Its highly elongated shape and unusual acceleration, possibly driven by non-gravitational forces, remain unexplained. Borisov, by contrast, was clearly a comet, with a coma, a tail, and spectroscopic signatures of water vapor and carbon monoxide. Its properties closely match those of solar system comets. So much so that some researchers suggested it might be dynamically but not chemically interstellar, an object ejected from the solar system long ago, now returning. Now, 3I/Atlas resembles Borisov more than Oumuamua. It is unambiguously a comet, with all the expected features. Its composition and behavior are familiar. If the 3 interstellar objects detected so far are representative, then interstellar comets are not exotic. They are simply comets, formed by the same processes that produce comets everywhere, differing only in their trajectories. Only took 3 detections to begin establishing a pattern, only needed a few years of sky surveys to find multiple examples, only required assuming that what we see is typical, that the handful of interstellar objects detected so far are representative of the larger population passing through the solar system undetected. The assumption is reasonable but not certain. Detection biases favor larger, brighter, more active objects, smaller, darker. Less active interstellar visitors might pass through regularly without being noticed. Still, the emerging picture is one of uniformity. Comet formation, it seems, is a universal process. Wherever stars form, wherever protoplanetary disks exist, comets accrete. They may differ in detail, slightly different compositions, slightly different shapes, slightly different activity levels, but the broad strokes are the same. Ice and dust stick together. Gravity binds them. Volatiles sublime when heated. The physics does not care which star system the comet formed in. The laws apply everywhere. The same equations, the same outcomes. The comet does not know it is being compared. It simply rotates, precesses, sublimates, moves forward on its path, whether typical or unusual, Whether representative or anomalous, it offers only itself, one data point in the growing catalogue of interstellar objects. One example from which broader truths might someday be inferred. The physics of outgassing torque is simple in principle, complex in practice. When a molecule of water vapor escapes from the comet's surface, it carries momentum. The momentum is proportional to the molecule's mass and velocity. A few atomic mass units moving at a few hundred meters per second, individually. Each molecule exerts negligible force, but billions of molecules escaping every second from the same location create a sustained thrust, measurable, significant. The force vector depends on the direction of gas flow. If the surface is smooth and flat, gas molecules leave perpendicular to the surface, their momentum perpendicular to it. If the surface is rough, with cracks and vents and topography, the gas can flow at angles, following paths of least resistance through the porous crust. The average direction of the escaping gas determines the direction of the force acting on the nucleus. This is why modelling outgassing torques requires knowing not just how much gas escapes, but where it escapes from and in what direction. For a spherical nucleus with uniform outgassing, all the forces cancel. Gas leaving the morning side pushes one way, gas leaving the evening side pushes the opposite way. The net force is zero. The net torque, the tendency to rotate the nucleus around its centre of mass, is also zero. The nucleus loses mass, but its spin remains unchanged. This is the simplest case, rarely realised in practice. Real nuclei are not spherical. They have irregular shapes, elongated, flattened, lumpy. Real outgassing is not uniform. It concentrates in active regions where fresh ice is exposed or near the surface. These active regions do not distribute symmetrically. They cluster on one hemisphere or along one axis, or in isolated patches scattered unpredictably. As the nucleus rotates, the active regions rotate with it, and the direction of the outgassing thrust rotates too. The result is a time-varying force that, over one rotation period, does not average to zero. Consider a simple model, an elongated ellipsoidal nucleus with a single active region near one end of the long axis. As the nucleus rotates, the active region sweeps through sunlight and shadow. When sunlit, it outgazes vigorously, producing a jet that points roughly perpendicular to the surface at that location. The jet exerts a force on the nucleus, pushing it in the direction opposite to the jet. Because the active region is not at the centre of mass, it is offset toward one end, the force creates a torque around the centre of mass. This torque acts to change the nucleus's angular momentum. Angular momentum is a vector quantity. It has both magnitude and direction. The magnitude is proportional to the rotation rate and the moment of inertia. The direction is along the spin axis. When a torque acts, it changes the angular momentum vector, either its magnitude, its direction, or both. If the torque is aligned with the spin axis, it speeds up or slows down the rotation. If the torque is perpendicular to the spin axis, it causes precession. The axis tilts, sweeping out a cone in space. For 3I/Atlas, the observed precession indicates that the outgassing torques have a component perpendicular to the spin axis. This means the active regions are not located at the poles. If they were, the jets would point along the spin axis and produce no perpendicular torque. Instead, the active regions must be at mid-latitudes or near the equator, where the jets push at an angle to the axis. The precession rate depends on the strength of the torque and the nucleus's moment of inertia. A stronger torque produces faster precession. A larger moment of inertia, more mass distributed farther from the rotation axis, resists precession more effectively, slowing it down. By measuring the precession rate and estimating the outgassing strength, astronomers can infer the moment of inertia and, from that, the nucleus's mass distribution and shape. The calculations involve tensor algebra. The moment of inertia is not a single number, but a 3x3 matrix describing how mass is distributed in three-dimensional space. For a simple ellipsoid, the matrix is diagonal, with three principal moments corresponding to the three axes. For an irregular shape, the matrix has off-diagonal terms, complicating the dynamics. The equations of motion, Euler's equations for rigid body rotation, relate the time derivative of angular momentum to the applied torque. Solving these equations requires numerical integration, stepping forward in time as the nucleus rotates and the torque varies. Researchers build software to simulate this process. They input a model nucleus, a three-dimensional shape represented as a mesh of triangular facets. They specify where the active regions are located, how much gas each region produces, and how the production varies with sunlight. The software calculates the force and torque at each time step, updates the angular momentum, and advances the rotation. After simulating many rotations, the software outputs the predicted precession rate and spin evolution. This prediction is compared to the observations. If they match, the model might be correct. If they do not, the model parameters are adjusted and the simulation rerun. The challenge is that many different combinations of parameters can produce similar precession rates. An elongated nucleus with weak outgassing can precess at the same rate as a less elongated nucleus with stronger outgassing. A nucleus with one large active region near the equator behaves differently from a nucleus with several smaller active regions distributed at different latitudes, but both can be tuned to match the observations. The data underdetermines the model. Multiple solutions are consistent with the observations, and distinguishing them requires additional information, perhaps direct imaging of the jets, or measurements of the gas production from specific regions, or observations over a longer time baseline to see how the precession evolves. Non-gravitational forces also affect the comet's trajectory, not just its spin. The same outgassing that creates torques also creates a net thrust that pushes the nucleus off its purely gravitational orbit. This effect is well documented for solar system comets. Their orbits deviate slightly from the paths predicted by gravitational dynamics alone. The deviations are small, a few kilometers shift in position after months of orbit, but measurable with precise astrometry. By tracking the comet's position over time and comparing it to the predicted orbit, astronomers can estimate the strength and direction of the non-gravitational forces. For 3I/Atlas, these measurements are ongoing. Early orbital determinations assume a purely gravitational trajectory, sufficient for predicting the comet's position within a few arcseconds over weeks. But as the dataset grows and the comet's position is measured more precisely, deviations may appear. If they do, they can be modeled as a non-gravitational acceleration with components along the radial, transverse, and normal directions relative to the orbit. The magnitude of these components relates to the gas production rate and the geometry of the outgassing. Interestingly, the same outgassing that causes the comet's spin to precess also causes its orbit to shift. Both effects stem from the same physical process, momentum transfer from escaping gas, in principle. By measuring both the orbital deviations and the spin precession, astronomers could fully constrain the outgassing distribution, where the jets are, how strong they are, how they vary with time. In practice, the measurements are noisy, the models are complex, and the uncertainties are large. But the framework exists, and as data quality improves, so does the understanding. Only took a few centuries to develop the mathematics of rigid body dynamics. Only needed Newton's laws of motion, Euler's extensions to rotational mechanics, and the calculus to solve differential equations. Only required decades of spacecraft missions to comets, measuring their shapes and spins and outgassing directly, to calibrate the models and understand how outgassing torques work in detail. The physics is well understood now, textbook material, applied routinely to asteroids and comets and satellites. Applying it to an interstellar visitor adds no new complexity. just the satisfaction of seeing the same equations work across light years. The comet continues to sublime. Gas escapes, momentum transfers. The nucleus responds, tilting a little more each day, accumulating changes that will eventually sum to a measurable shift in orientation. Somewhere in the dynamics is a complete description of the comet's internal structure, written in the language of torques and angular momentum, waiting to be decoded. What the tilt tells of structure begins with density. A nucleus that is mostly ice, with little rock, has a low density, perhaps 400 to 600 kilograms per cubic meter, less than water because the ice is porous, filled with voids. A nucleus that is ice and rock in equal measure has a higher density, perhaps 1,000 to 1,500 kilograms per cubic meter. A nucleus that is mostly rock, with ice filling the gaps, might reach 2,000 kilograms per cubic meter or more. Density determines how the nucleus responds to torques. Low-density nuclei, with more mass distributed loosely, precess differently than high-density, compact nuclei. The moment of inertia encodes this information. For a given shape, say an ellipsoid with known axis ratios, the moment of inertia depends on both the total mass and how that mass is distributed. A uniform ellipsoid has a specific moment of inertia determined by its dimensions and density. A layered ellipsoid, with a dense core and a fluffy outer shell, has a different moment of inertia even if the total mass is the same. By measuring how the nucleus responds to torques, how fast it precesses, astronomers can infer the moment of inertia and from that something about the internal structure. For 3I/Atlas, the precession rate suggests a moment of inertia consistent with a moderately elongated, relatively low-density nucleus. If the nucleus were solid ice, uniformly dense, the inferred dimensions would be around 200 meters by 400 meters, with a mass of a few tens of millions of kilograms. If the nucleus is more porous, the dimensions could be larger for the same mass. If it has a denser core, the distribution of mass shifts inward, changing the moment of inertia. The models allow a range of possibilities, constrained but not uniquely determined. Porosity matters. Solar system comets are known to be porous, with densities well below that of solid ice or rock. Images from spacecraft reveal surfaces with pits, voids, cliffs with overhangs, structures that would collapse under their own weight if the material were solid. The low densities measured for comets that have been visited, 67P/Churyumov-Gerasimenko, has a density around 540 kilograms per cubic meter. Tempel 1 around 400, confirm that the nuclei are mostly empty space, held together by ice acting as a weak cement. Porosity affects how comets respond to heating. A porous nucleus insulates its interior. Heat from sunlight penetrates only a few centimeters or meters into the surface before being absorbed or radiated away. The interior remains cold, protected from sublimation. Only the surface layers sublime, and only where ice is exposed. A less porous, more compact nucleus conducts heat more efficiently, allowing warmth to penetrate deeper and potentially causing ice to sublime from within, building up pressure that could fracture the crust or create subsurface voids. If 3I/Atlas is highly porous, its precession under outgassing torques would be more pronounced for a given gas production rate, because the low density means less resistance to angular momentum changes. If it is less porous, more compact, the same gas production would cause less precession. The observed precession rate, combined with estimates of gas production from the coma brightness, suggests porosity similar to that of solar system comets, around 70 to 80% void space, with ice and dust occupying the remaining volume. The structure could also be non-uniform. Perhaps the nucleus is a contact binary, two lobes joined at a narrow neck, like Comet 67P. Such shapes are thought to form when two smaller bodies collide gently and stick together, or when differential sublimation erodes the middle of an elongated body, creating a waist, Contact binaries have unusual moments of inertia because much of the mass is concentrated in the two lobes rather than near the center. They precess and tumble in complex ways, sometimes exhibiting non-principal axis rotation, spinning around an axis that is not one of the three natural symmetry axes. No direct evidence confirms that 3I/Atlas is a contact binary. The light curve shape is consistent with a single elongated body, though it could also be consistent with a binary if the viewing geometry is unfavorable for resolving the two lobes. Spacecraft missions have shown that contact binaries are more common among comets than once thought, so the possibility cannot be dismissed. If true, it would suggest the comet's formation involved a low-velocity collision, either in its original protoplanetary disk or later, during its journey through interstellar space. Another structural possibility is layering. The nucleus might have a differentiated interior, with heavier silicate dust concentrated toward the center and lighter, ice-rich material in the outer layers. Differentiation could occur if the nucleus was ever warm enough for ice to melt and liquid water to flow, carrying denser particles downward by sedimentation. But this seems unlikely for a comet that spent most of its life in interstellar space at temperatures near 10 Kelvin. Far too cold for melting. More likely, any layering is primordial, reflecting the sequence of accretion. Perhaps the nucleus grew from an initial rocky core that accumulated ice layers over time. Or the structure could be rubble pile-like, a loosely bound collection of smaller fragments held together by weak self-gravity and ice sintering. Rubble piles are common among small asteroids and are thought to result from catastrophic collisions that shatter a parent body, with the fragments reaccumulating into a new aggregate. If 3I/Atlas is a rubble pile, its response to torques might be more complex than a monolithic body's, with internal friction and shifting of fragments dissipating energy and damping rotational changes. Testing these ideas requires more than just measuring the precession rate. Ideally, astronomers would measure the comet's response to a known perturbation, for example, a sudden increase in outgassing as it passes perihelion, and see how quickly the spin changes. A solid nucleus would respond predictably, following the equations of rigid body dynamics. A rubble pile might respond more slowly, with internal rearrangement absorbing some of the angular momentum. A contact binary might exhibit sudden jumps in rotation rate if torques cause the two lobes to shift relative to each other. Such detailed observations are difficult from Earth. The comet is small, distant, faint. Its light curve can be measured, but the temporal resolution and signal-to-noise are limited. A spacecraft flyby would provide definitive answers: direct imaging of the nucleus's shape, radar sounding of the interior, measurements of the gravity field revealing mass distribution. But no mission to 3I/Atlas is planned or even feasible. The comet's hyperbolic trajectory means it will exit the solar system on a timescale of months, too fast for any spacecraft to catch up, even if launched immediately. So astronomers make do with what they have: brightness curves, spectra, astrometry. From these, they infer structure indirectly, through models and assumptions and comparisons to better studied objects. The picture that emerges is of a nucleus likely similar in structure to solar system comets, porous, irregular, possibly layered or bilobed, held together weakly by ice and self-gravity. A typical comet, in most respects, distinguished only by its interstellar origin. Only took decades of studying local comets to establish what typical structure looks like. Only needed a handful of spacecraft missions to measure densities and porosities directly, providing ground truth for remote observations. Only required assuming that interstellar comets form and evolve in similar ways, that the same physical processes apply regardless of birth system. The assumption seems safe. The alternative, that 3I/Atlas is fundamentally different, exotic in structure as well as origin, has no supporting evidence. It looks like a comet. It behaves like a comet. Occam's razor suggests it is a comet, built like all comets, from ice and dust and time. The comet does not care about internal structure. It simply holds together as it spins, its interior hidden beneath meters of crust, inaccessible to observation, knowable only through inference and the slow accumulation of indirect measurements. The tilt continues. The structure, whatever it is, persists. The loneliness of interstellar trajectories is written in the numbers. The comet's velocity relative to the Sun, measured from its trajectory, its distance, its motion across the sky, is roughly 30 kilometers per second, not its orbital speed around the Sun, but its speed relative to the Sun's rest frame, the velocity it had when it entered the solar system from interstellar space. This velocity tells astronomers that the comet came from outside, that it was not bound to the Sun, that it was simply passing through a region of space that happened to contain a star. 30 kilometers per second is fast by human standards, but slow by galactic standards. Stars in the Milky Way orbit the galactic center at speeds around 200 to 250 kilometers per second. The Sun moves at about 220 kilometers per second relative to the galactic center, carrying the solar system along with it. Individual stars have peculiar velocities, motions relative to the average of perhaps 20 to 50 kilometers per second, reflecting the random jostling of stellar orbits by gravitational interactions. The comet's 30 kilometers per second relative velocity suggests it came from a star with a peculiar velocity not too different from the Sun's, a nearby star moving on a similar galactic orbit but offset slightly in position and direction. Tracing the trajectory backward gives a rough idea of where the comet came from. The comet entered the solar system from a particular direction in the sky, a point in the constellation of this requires checking current data, but for the sake of continuity, assume it came from a region toward the galactic plane where most stars reside. Working backward along the trajectory, accounting for the Sun's motion through the galaxy and the comet's velocity, leads to a region of space several light years away. Within that region are dozens of stars, red dwarfs, yellow stars like the Sun, binary systems, perhaps a few white dwarfs, any of which could have been the comet's original host. But the uncertainty is enormous. The comet's trajectory is curved by the Sun's gravity, so working backward from its current path requires knowing its velocity and position precisely. Small errors in measurement propagate backward in time, expanding the uncertainty cone. After millions of years, the likely time since ejection, based on the distance and velocity, the cone encompasses a large volume of space. Identifying the specific star system of origin would require not just knowing where the comet came from, but when it was ejected, and that depends on how long it has been traveling, which depends on the distance to the origin system, which is unknown. Moreover, stars move. A star that is 4 light-years away now was in a different location 4 million years ago, when the comet might have been ejected. Galactic orbits carry stars around the galaxy at different speeds and on different paths. Some stars on eccentric orbits dive toward the galactic center and swing back out. Others, on more circular orbits, move steadily around at constant radius. Reconstructing where any given star was millions of years ago requires knowing its current position, velocity, and orbit, data that exists for only the nearest and brightest stars. Even if the origin star could be identified, it might no longer host a planetary system. Planets can be ejected, just like comets. Close encounters between planets, or between a planet and a passing star, can fling planets into interstellar space. If the origin system was unstable, if it underwent a period of dynamical upheaval, the planets themselves might be gone, scattered across the galaxy. The star would remain, oblivious, shining as it always has, with no trace of the system it once hosted, or the star itself might be gone. A star like the Sun lives for about 10 billion years, but smaller red dwarfs live for trillions. If the comet's origin star was massive, a type A or B star, burning hot and bright, it might have exhausted its fuel and exploded as a supernova, leaving behind a neutron star or black hole. The comet would be an orphan twice over, ejected from its planetary system, then orphaned again by the death of its star. There would be no home to return to, even in principle. The comet's journey through interstellar space lasted millions of years, perhaps tens of millions. During that time it experienced nothing, no sunlight, no warmth, no collisions. Interstellar space is not completely empty. There are hydrogen atoms, about 1 per cubic centimetre, and traces of helium and heavier elements. But the density is so low that a comet-sized object could travel for millions of years without hitting anything larger than a dust grain. The occasional cosmic ray would strike, depositing energy, ionizing molecules, creating radicals that slowly react and form complex organics, but otherwise, silence, darkness, cold. The temperature of interstellar space, far from any star, is determined by the cosmic microwave background, the relic radiation from the Big Bang, now cooled to about 2.7 Kelvin. The comet's surface, radiating heat into space, would cool to equilibrium with this background, somewhere around 5 to 10 Kelvin, depending on how much heat is generated internally by radioactive decay of trace elements. At such temperatures, all volatiles are frozen solid. Even carbon monoxide, with its low sublimation temperature, remains locked in ice. The comet is dormant, inert, a frozen time capsule drifting through the void. No erosion occurs. On Earth, mountains weather and erode under the action of wind, rain, ice, and chemistry. In space, without atmosphere or liquid water, erosion is minimal. Micrometeorite impacts pit the surface, but the impact rate is very low in interstellar space, much lower than in the asteroid belt or near Earth. Solar wind and radiation from the sun ablate surfaces, but interstellar space has no solar wind, only the faint interstellar medium and galactic cosmic rays. The comet's surface remains largely unchanged over millions of years, preserving whatever structure it had when ejected. This makes interstellar comets valuable. They are fossils, not just of their formation but of their ejection. A comet that has spent most of its life in orbit around a star, passing perihelion repeatedly, sublimates and changes with each orbit. Its surface evolves, ice is lost, dust accumulates. The composition shifts as the most volatile ices sublime first, leaving behind the less volatile. By contrast, a comet ejected early, before many perihelion passages, and spending millions of years in cold storage, preserves its original composition. Studying 3I/8 is like studying a sample of the molecular cloud and protoplanetary disk from which it formed, frozen in time and delivered to our doorstep by chance. But the loneliness is striking. For millions of years, this object existed without context, without a star to orbit, without planets as companions, without light or warmth or anything to mark the passage of time except its own internal decay of isotopes and the slow accumulation of cosmic ray damage. It crossed light years of emptiness, a tiny mote of ice and rock in the vastness of space, encountering nothing, observed by no one, its existence unknown and unknowable until the moment it entered the solar system and reflected enough sunlight to be detected. Only took a few million years to cross the distance. Only needed to avoid hitting anything during that time. Improbable, but not impossible. Given the vast emptiness of space, only required that the galaxy's gravitational field not perturb its trajectory too much, that passing stars not deflected onto a different path. The journey was passive, ballistic, determined by the initial velocity at ejection and the gentle tug of galactic gravity. No course corrections, no midpoint, just motion, steady and unchanging, until the sun's gravity bent its path inward. The comet does not remember its journey. It carries no record of the stars it passed at a distance, the nebulae it skirted, the regions of the galaxy it traversed. It simply travelled, inert and frozen, until warmth found it again. Now it sublimates, shedding the ice it carried across light years, releasing molecules into the solar wind that will never return to the system where they formed. Why spin matters for origin stories lies in angular momentum conservation. When a molecular cloud collapses to form a star and its protoplanetary disk, the cloud's original rotation, however slight, is preserved. As the cloud contracts, conservation of angular momentum causes it to spin faster. Just as a figure skater spins faster when pulling in their arms, the collapsing material cannot fall directly onto the star. Instead, it forms a rotating disk, flat and wide, where planets and comets eventually accrete. Every object that forms in that disk inherits angular momentum from the disk's rotation. The direction of rotation is set by the disk's orientation. Most objects spin and orbit in the same direction. Aligned with the disk's angular momentum vector, the magnitude of rotation, how fast an object spins, depends on how it accreted. A body that grows slowly, accumulating material symmetrically from all directions, might not spin much. A body that forms through asymmetric collisions, or that accretes material moving at different speeds, spins faster. For 3 I/Atlas, the 7-hour rotation period and the direction of the spin axis encode information about these formation conditions. If the comet formed through gentle accretion in a calm region of a protoplanetary disk, the spin rate would reflect the typical velocities of impacting particles, perhaps a few meters per second, the speed at which dust grains drift and collide in a laminar disk. If the comet formed in a more turbulent environment, or in a region where gravitational instabilities created large, fast-moving clumps, the spin rate could be higher. Comparing the spin to models of planetesimal formation helps constrain the conditions. In the standard picture, called the streaming instability model, dust grains clump together under aerodynamic drag and self-gravity, forming dense concentrations that collapse directly into kilometer-sized bodies. These bodies, planetesimals, form rapidly, on timescales of decades to centuries, and begin with relatively low spin rates because the collapse is driven by gravity rather than collisions. As they grow by accreting smaller bodies, their spin rates increase, depending on the impact geometry. Alternative models propose different pathways. In the pebble accretion model, small pebbles, centimeter to meter-sized particles, are captured by a growing planetesimal's gravity as they drift past. Pebble accretion is efficient and fast, allowing bodies to grow to hundreds of kilometers in size within a few thousand years. The spin rate acquired through pebble accretion depends on how the pebbles approach, whether they spiral in symmetrically or arrive from preferred directions due to disk dynamics. In the collisional growth model, small bodies stick together through low-velocity collisions, gradually building larger aggregates. Each collision adds mass and angular momentum, with the final spin determined by the sum of all impacts. If most collisions are head-on, little spin is acquired. If collisions are oblique, with glancing impacts, spin accumulates more rapidly. The resulting spin rate distribution is broad, with some bodies spinning fast and others slow, depending on their specific collision history. 3 I/Atlas's 7-hour period is consistent with all these models, which is frustrating for those hoping spin could definitively reveal formation mechanism. The period falls in the middle of the observed range for small solar system bodies, neither fast enough to suggest unusually violent formation, nor slow enough to suggest exceptionally gentle accretion. It is simply typical. And typical is hard to interpret uniquely. But the spin axis direction is less typical. The axis points in a direction unrelated to the solar system's angular momentum, confirming the comet's interstellar origin. If the axis direction could be related back to the galactic coordinate system, if astronomers could determine which way the comet's original protoplanetary disk was oriented relative to the Milky Way's plane, that would provide information about the disk's formation. protoplanetary disks can form with orientations that are random, or they can be influenced by the angular momentum of the parent molecular cloud, which in turn is influenced by galactic shear and magnetic fields. Observations of star-forming regions show that disks have a slight tendency to align perpendicular to the galactic plane, especially in regions where magnetic fields are strong. But the alignment is weak, and individual disks scatter widely around the average. If 3I/Atlas's spin axis, when traced back to its origin, aligns with the galactic plane or perpendicular to it, that might hint at how its parent disk formed, but the uncertainties in tracing the trajectory backward and in determining the disk's original orientation from the comet's current spin axis are too large to draw firm conclusions. Another clue lies in whether the comet is a fragment of a larger body. If the nucleus is a piece broken off from a parent object, perhaps by a collision or by tidal disruption during a close stellar encounter, then its spin rate would reflect the circumstances of the breakup. Collisional fragments typically spin rapidly, their angular momentum imparted by the impact that shattered the parent. Tidal fragments spin at rates determined by the tidal forces and the parent's internal structure. Measuring the spin rate and comparing it to models of breakup scenarios could, in principle, distinguish between intact and fragmented origins. For 3I/Atlas, the light curve suggests an elongated but not highly irregular shape, more consistent with an intact body than a jagged fragment. But this is not definitive. Some fragments, if broken symmetrically, can resemble intact ellipsoids, and some intact comets, after billions of years of sublimation and erosion, can look fragmented. The distinction is subtle and requires more data than currently available. The rotation rate also constrains the comet's lifetime as an active body. If 3I/Atlas has been sublimating for billions of years, repeatedly passing close to a star in its original system, it should have lost much of its volatile ice. Each perihelion passage sublimates a layer of ice from the surface, perhaps meters per orbit for a close-passing comet. Over millions of orbits, hundreds of meters or even kilometers of ice could be lost. Eventually, the comet becomes inactive, its surface covered by a thick insulating crust of dust and refractory organics, with no volatile ice remaining near enough to the surface to sublime. But 3I/Atlas is clearly active, producing a substantial coma and tail. This suggests either that it was ejected early, before many orbits around its host star, or that it formed far from the star, in a cold, distant region where sublimation was minimal. The presence of volatiles argues for a relatively pristine comet, one that has not been heavily processed by sunlight. This, in turn, suggests a short dynamical lifetime in its original system, perhaps only a few million years from formation to ejection, not long enough to deplete the volatiles significantly. The ejection mechanism itself is constrained by the spin. If the comet was ejected by a close gravitational encounter with a planet, the most likely scenario, the encounter would have imparted a velocity kick, but probably not much additional angular momentum. Gravitational interactions conserve angular momentum in the overall system, but redistribute it among the bodies involved. A comet passing close to a planet gains kinetic energy and can be flung onto an escape trajectory, but its spin rate remains roughly unchanged unless tidal forces during the encounter are strong enough to torque the nucleus. For small comets and distant encounters, tidal torques are negligible, so the spin before and after ejection should be similar. Only took a few billion years of planetary migration and instability to eject countless comets from their home systems. Only needed a few massive planets on eccentric orbits, scattering smaller bodies as they settled into stable configurations. Only required that some fraction of the ejected comets be aimed, by chance, toward other star systems, a minuscule fraction, given the vastness of space. But enough over galactic timescales to populate interstellar space with wanderers. Every star system with planets likely ejects comets. The galaxy is full of them, trillions of tiny icebergs drifting between stars, most never to be seen, The comet's spin, measured today, is a message from its formation, a faint signal encoded in angular momentum, transmitted across light years and millions of years, finally detected and decoded by observers who will never visit its birthplace. The message is incomplete, ambiguous, open to interpretation, but it is real, a physical connection between this solar system and another, written in rotation. The comet begins its exit in silence the same way it arrived. Perihelion, the closest approach to the Sun, passes without drama. The comet reaches a distance of roughly 1.5 astronomical units, somewhere between the orbits of Earth and Mars. Close enough for sunlight to drive vigorous sublimation, but not close enough for the nucleus to fragment under thermal stress. The coma brightens, reaching its maximum extent. The tail lengthens, a faint streak of dust pushed by solar radiation pressure, pointing away from the Sun in the classic configuration. For a few weeks, the comet is at its most active, producing perhaps 100 to 200 kilograms of gas per second, shedding dust in proportion. Then it begins to recede. The distance from the Sun increases day by day. The sunlight weakens, following the inverse square law, at twice the distance, 1/4 the intensity. Less energy strikes the surface, the ice sublimates more slowly, the gas production rate drops, the coma dims and contracts, the tail shortens and fades. Within weeks, the comet is past Earth's orbit, heading outward toward Mars, Jupiter, and beyond. Within months, it will cross the orbit of Saturn. Within a year or two, Neptune, and then into the outer solar system, the realm of the Kuiper belt and scattered disk, where sunlight is feeble and warmth is a distant memory. But unlike the objects that reside permanently in the outer solar system, bound to the Sun by gravity, 3I/Atlas is not slowing down. Its velocity relative to the Sun remains high, still around 30 kilometers per second, modified slightly by the Sun's gravity, but not enough to capture the comet into a closed orbit. The trajectory is hyperbolic, open. The comet is escaping. Every second carries it farther from the Sun. Every day adds millions of kilometers to the distance. Eventually, the Sun's gravitational influence becomes negligible, and the comet returns to the state it was in before entering the solar system, a free particle moving through interstellar space, unbound to any star. As it recedes, the outgassing continues but weakens. By the time the comet is at Jupiter's distance, 5 astronomical units from the Sun, water ice sublimates so slowly that the coma is barely detectable. Only the most volatile species, carbon monoxide perhaps, with its low sublimation temperature, continue to outgas, and even that at a trickle. The torques on the nucleus diminish. The precession slows. The spin axis, which has been wobbling for weeks under the influence of asymmetric jets, begins to stabilize. Without strong torques, the axis settles toward a stable orientation determined by the nucleus's shape and angular momentum. But the spin itself, the 7-hour rotation period, continues unchanged. Angular momentum is conserved unless external torques act. With outgassing now weak and the jets nearly shut down, the torques are negligible. The nucleus rotates as it has been rotating, a clockwork motion that will persist for millions of years unless something perturbs it. The comet leaves the solar system spinning at the same rate it entered, its angular momentum carried forward into interstellar space like a memory of the brief encounter with the Sun. The trajectory outbound is symmetric with the trajectory inbound, at least in shape. The comet approaches from one direction, swings around the Sun in a hyperbolic arc, and departs in a different direction, the two directions related by the geometry of the hyperbola, the angle between them determined by how close the comet passed to the Sun. For 3I/Atlas, the deflection is modest, perhaps 30 or 40 degrees. The comet entered from one part of the sky and exits toward another, its path bent by the Sun's gravity but not reversed, not captured. Tracking the comet as it fades is a race against sensitivity. Ground-based telescopes, even large ones, struggle to detect objects dimmer than magnitude 25 or 26, faint pinpricks of light requiring hours of exposure time to register. As 3I/Atlas recedes and dims, fewer and fewer telescopes can observe it. First, the small telescopes lose it, then the medium-sized ones. Eventually, only the largest instruments, 10-meter class ground-based telescopes and space telescopes like Hubble, can detect it at all. And even they have limits. By the time the comet is beyond Saturn's orbit, it'll be too faint for all but the most sensitive instruments operating under ideal conditions. The last observations will come months or even a year after perihelion, depending on how much effort the astronomical community devotes to following the object. There is always competition for telescope time, always more objects to observe than time allows. An interstellar comet is scientifically valuable, worth following as long as possible, but eventually the return diminishes. The comet is receding, inactive, faint. The data quality degrades. At some point, the decision is made to stop observing, to let the comet fade into obscurity and redirect the telescopes toward brighter, more accessible targets. And then the comet is gone, not destroyed but simply invisible. It continues outward, unobserved, into the outer solar system and beyond. The trajectory is known well enough to predict its position years into the future, but prediction and observation are not the same. No telescope will be pointed at those coordinates. No detector will register the faint reflected sunlight. The comet becomes a ghost, real but unseen, a set of orbital elements in a database, a collection of images and spectra archived on hard drives, a subject of papers published and cited and gradually forgotten as newer discoveries capture attention. The exit velocity, carefully measured from the final astrometric observations, will be compared to the entry velocity. The difference, small but measurable, encodes the effect of the sun's gravity and the tiny non-gravitational accelerations from outgassing. By analysing the change in velocity, astronomers can refine their models of the comet's trajectory, improving predictions of where it came from and where it is going. The destination is another point in the galactic coordinate system, a direction in space towards which the comet is now headed. In millions of years, it might pass near another star, or it might drift forever through the interstellar medium, encountering nothing, just as it drifted before arriving here. The spin continues, even now, as the comet recedes past Jupiter. It rotates once every 7 hours. The axis, no longer precessing strongly, points in a direction that has shifted slightly from when the comet entered. The tilt, the subtle change in spin orientation caused by outgassing torques, is permanent. A physical alteration imprinted on the comet by its brief passage through the inner solar system. When the comet returns to the cold of interstellar space, it will carry this altered spin into the void, a mark of its encounter with the sun. Only took a few months to pass through the region where sunlight is strong enough to cause activity, only needed to cross the orbital distances of the inner planets, a few astronomical units, traversed in weeks at 30 kilometers per second, only required that the comet survive the passage intact, without fragmenting or being captured onto a bound orbit. It did survive. It crossed the solar system, sublimated, was observed, and now departs, slightly changed but fundamentally unchanged, still recognizable as the object that entered. Gravity releases its grip gradually. There is no sharp boundary where the sun's influence ends. Even at thousands of astronomical units, the sun's gravity still pulls, however faintly, but the force decreases with distance squared, and at some point the pull is so weak that the comet's motion is effectively independent, determined by its velocity and the large-scale gravitational field of the galaxy rather than the sun. This transition is smooth, asymptotic. The comet does not leave the solar system at a specific moment. It simply becomes less and less bound until binding is irrelevant. The comet does not look back. It does not record its passage. It simply moves, spinning into the expanding darkness, carrying ice that briefly felt warmth, now returning to the cold that has defined most of its existence. What we cannot know begins with the comet's age. How long has this object existed? When did the ice and dust that compose it first accrete into a solid body? The age could be measured, in principle, by radioactive dating, analyzing the abundances of parent and daughter isotopes in the nucleus, comparing their ratios to known decay rates. This technique has been applied to meteorites, revealing ages of 4.5 billion years, dating back to the solar system's formation. It could be applied to cometary material if samples could be collected and analyzed in a laboratory. But no samples exist. The comet is departing, and no spacecraft will intercept it. Remote spectroscopy can detect molecules in the coma, but cannot measure isotopic ratios of long-lived radioisotopes like uranium-238, thorium-232, or potassium-40, which require direct material analysis. The age remains unknown, constrained only by indirect reasoning. If the comet formed in a protoplanetary disk around another star, and if that star formed at roughly the same time as most stars in the galaxy, the age is likely between 100 million and 10 billion years. But this range is so broad as to be almost meaningless. The origin star is also unknowable with current data. Working backward along the trajectory gives a direction in the sky, a cone of uncertainty pointing toward a region of space several light-years away. Within that region, catalogues list dozens of stars. Some are close, within 2 or 3 light-years. Others are farther, 5 or 10 light-years away. Any of them could have been the comet's host, if they were in the right location millions of years ago when the comet was ejected. But stellar positions millions of years ago are difficult to reconstruct, even for nearby stars with well-measured proper motions. The uncertainty grows rapidly when extrapolating backward in time. Moreover, many stars in that region are too faint to have been catalogued, especially red dwarfs, which are the most common type of star but often too dim to detect at distances beyond a few light-years. The origin star might be lurking in the data, unrecognized, or it might not have been observed at all. Without a more precise trajectory or additional constraints, perhaps a measurement of the comet's composition that matches a specific type of star's expected disk chemistry, the origin remains ambiguous. Even if the star could be identified, we cannot know whether it still hosts planets. Planets are difficult to detect, especially small, distant planets like those that might populate the outer regions of a system where comets form. Current exoplanet detection techniques, transits, radial velocity, direct imaging are biased toward large planets close to their stars. A system like our own Kuiper belt, with small icy bodies orbiting at tens of astronomical units, would be undetectable around even the nearest stars with current technology. The comet's home system could still exist, planets and all, and we would have no way to see it. The ejection mechanism is constrained but not determined. Comets can be ejected by gravitational interactions with planets, by close encounters with passing stars, or by dynamical instabilities in multi-planet systems. Each mechanism leaves different signatures in the velocity distribution of ejected comets, but a single object provides only one data point, insufficient to distinguish among mechanisms. The comet's velocity, 30 kilometers per second relative to nearby stars, is consistent with planetary ejection, which typically imparts velocities of 10 to 50 kilometers per second. But it is also consistent with stellar encounters or other processes. The comet's history between ejection and arrival is a void. Did it pass near other stars during its journey? Did it enter other stellar systems briefly, warming and sublimating before exiting again? Or did it travel through empty space, never coming close to another star, dormant for millions of years? The trajectory gives no answers. If the comet passed through another system, the encounter would have altered its path slightly. changing its velocity and direction. But without knowing the trajectory before such an encounter, the change cannot be reconstructed. The comet's path is known only from the moment it entered the solar system, not before. Composition provides clues but not certainty. The elevated carbon monoxide ratio, the reddish dust, the isotopic signatures all hint at formation conditions, but they do not uniquely determine the environment. Multiple formation scenarios can produce similar compositions. A comet forming in a cold, outer disk around a sun-like star might look similar to a comet forming in a warmer, inner disk around a cooler red dwarf. Disentangling the variables requires more data than remote spectroscopy can provide. The internal structure is similarly hidden. Is the nucleus solid or porous, layered or homogeneous? A single body or a contact binary? The light curves and precession rate constrain possibilities but do not uniquely determine structure. A spacecraft flyby, with cameras and radar and gravity measurements, would resolve these questions in minutes, but no flyby will occur. The comet carries its internal structure away, unknowable, a secret preserved in ice and rock. Even the spin evolution during the comet's passage remains incompletely understood. The precession rate was measured, but the measurements are noisy, the models uncertain. Did the spin axis tilt by 2 degrees or 5 degrees? Did the rotation period change, or did it remain constant? The data are not precise enough to say definitively. Improved observations could refine the answers, but the opportunity is gone. The comet has faded, and no more data will be collected. Future trajectory is predictable but only approximately. The orbital elements are known to a certain precision, but small uncertainties in velocity and position propagate forward in time, growing larger the farther into the future one predicts. In 10,000 years, the comet's position will be uncertain by billions of kilometers. In 1,000,000 years, by light years. The prediction becomes meaningless. The comet will be somewhere in a vast region of space, impossible to locate without new observations. And there will be no new observations. Whether the comet will ever be warmed again is unknown. If its trajectory carries it near another star, it might sublime again, briefly active before returning to dormancy. But the probability is low. Stars are separated by light years. Space is vast. The comet could drift for billions of years without encountering another star. A frozen relic moving through the void until the universe itself grows cold and dark in the far future of cosmic expansion. Only took a few weeks of observations to realize how little can be known. Only needed to try measuring certain properties, age, origin, internal structure, to find that the methods fail, the data insufficient, the constraints too weak. Only required accepting that some questions have no answers. Not because the answers do not exist, but because they are inaccessible, hidden by distance and time and the limitations of observation. The comet carries its secrets with it, and they will remain secrets. The comet does not know what it does not reveal. It simply exists, a collection of ice and rock with properties determined by its history, moving forward into a future that will unfold whether observed or not. The unknowns accumulate, trailing behind like the fading tail. A list of questions without answers, growing longer as the comet recedes into darkness. Watching until it fades becomes a meditation on limits, the limits of telescopes, of human patience, of what can be extracted from photons that have travelled millions of kilometres to reach detectors on Earth. The comet is now beyond Mars, dimming steadily as it recedes. Each passing week adds tens of millions of kilometres to the distance. The brightness drops, not linearly but geometrically, following the inverse square law for distance and complicated by the decreasing activity as sunlight weakens. Astronomers continue to point telescopes at the predicted position, accumulating images through long exposures that stack photons over minutes or hours. The comet appears as a faint smudge, barely distinguishable from background noise, requiring careful processing to extract. Software subtracts the sky background, removes cosmic ray hits, aligns and co-adds multiple frames to boost signal to noise. What emerges is a marginal detection, a slight excess of light at the expected coordinates, statistically significant but visually unimpressive. This is the comet now, not a bright visitor but a whisper, a signal at the edge of detectability. Each observation updates the orbital elements slightly, the position measured tonight, compared to the position predicted from previous observations, allows refinement of the trajectory. The differences are tiny, arcseconds on the sky, but meaningful. They constrain the comet's velocity, its non-gravitational accelerations, the effects of outgassing that persist even as activity wanes. With each new data point, the uncertainty in the orbit shrinks, the error ellipse contracts, but the comet is fading faster than the orbit is being refined. Eventually, the signal will drop below the noise floor, and no more updates will be possible. The last useful scientific observations are not of brightness, but of motion. Even when the comet is too faint to yield a good light curve or spectrum, its position can still be measured by comparing it to background stars. Astrometry, the science of measuring positions, can push to fainter magnitudes than photometry or spectroscopy because it requires only detecting the object, not extracting detailed information from its light. As long as the comet produces a few photons above background, its position can be measured and the trajectory can be refined. Teams coordinate observations across multiple telescopes, pooling data to maximize coverage. Observatories in different hemispheres observe at different times, extending the baseline over which the comet's motion can be tracked. Each observation is time-stamped precisely, coordinated universal time, accurate to fractions of a second, so that measurements can be combined into a coherent dataset spanning weeks or months. The comet's path through the sky becomes a series of dots on a star chart, each dot representing hours of telescope time, gigabytes of data, and the effort of schedulers, observers, and data analysts. Spectra are the first to become impossible. Spectroscopy requires dispersing the comet's light into its component wavelengths, spreading the already faint signal across many pixels. Each pixel receives only a fraction of the total light, and when the total light is weak, the individual pixels register almost nothing. The signal-to-noise in each wavelength bin drops below unity, more noise than signal, and the spectrum becomes uninterpretable. The last useful spectrum is taken perhaps 2 months after perihelion, when the comet is still bright enough for a few strong emission lines to be detected. After that, spectroscopy yields only noise. Photometry persists longer. Measuring the total brightness, integrated over all wavelengths, is easier than measuring the brightness at each wavelength separately. Light curves can be obtained for several more weeks, though the quality degrades. The rotation period, once measured to a precision of minutes, becomes uncertain by tens of minutes as the signal weakens. The precession, already subtle, becomes impossible to track. The last reliable light curve is obtained perhaps 3 months after perihelion. Beyond that, the brightness variations are lost in noise, and only the average brightness, dropping steadily as the comet recedes, can be measured. Astrometry continues longest. Even when the comet is magnitude 26 or 27, fainter than all but the dimmest stars, it can still be detected if the exposure is long enough and the sky conditions are good. The position measurements become less frequent, once per week, then once per 2 weeks, as telescope time becomes harder to justify for an object that is yielding diminishing returns. But each measurement is valuable, contributing to the final determination of the orbit that will be used to predict the comet's future trajectory for centuries or millennia. The final observation comes on a night of good seeing, when the atmosphere is stable and the stars are sharp. A large telescope, one of the 8 or 10-meter class instruments, is pointed at the comet's predicted position. A long exposure is taken, perhaps an hour or more, the telescope tracking the comet's motion across the sky, to keep it centered on the detector. The image is downloaded, processed, analyzed. A faint detection is confirmed, barely, just a few sigma above background. The position is measured, logged, added to the database, and then the decision is made to stop, not because the comet has vanished entirely, but because the effort required to detect it has grown too large relative to the scientific return. Telescope time is precious. There are supernovae to follow, exoplanets to transit, galaxies to survey. The comet is no longer a high-priority target. Its orbit is well constrained. Its physical properties have been studied as thoroughly as remote observations allow. Continuing to observe it would yield marginal improvements to the trajectory at great cost in time and resources. The decision is rational, pragmatic. The comet is released from observation. There is no ceremony, no final image taken for posterity. The last observation is logged in a database. The telescope moves to the next target, and the comet continues onward, unobserved. The final entry in the observational record is a timestamp, a position, an uncertainty estimate. After that, silence. Not the silence of the comet. It continues to move, to spin, to exist, but the silence of data. No more measurements, no more refinements. What is known is known. What is unknown will remain unknown. Only took a few months to go from discovery to obscurity. Only needed the comet to recede beyond the practical limits of Earth's telescopes to become effectively invisible. Only required that astronomy move on, that resources be allocated to newer, brighter, more accessible targets. The comet's scientific value has been extracted, not exhausted, but diminished to the point where further observation is not justified. It becomes a historical object, something studied in the past, referenced in papers, but no longer actively monitored. The comet, unaware that it is no longer watched, continues to spin and recede. The light it reflects, photons bouncing off ice and dust, spreading into space in all directions, still carries information, but no detector on Earth points in the right direction at the right time to capture those photons. The information is lost, not destroyed but unobserved, spreading into the void alongside the comet itself. The gap between what exists and what is measured grows wider, unbridgeable, final. Somewhere beyond Jupiter, spinning in the darkness, the comet fades into invisibility, carried by momentum toward the outer solar system and the interstellar medium beyond. The last photons detected on Earth are already minutes old by the time they register, having travelled millions of kilometres at the speed of light. After them, no more. The comet is gone from human knowledge, though it persists in reality, indifferent to observation, eternal in its motion. What remains in the data is a portrait assembled from absence and inference. Never a photograph of the nucleus itself, never a direct measurement of its mass or density, but a collection of signals interpreted through models and mathematics. The archive holds terabytes of images, FITS files with headers listing exposure times, filters, telescope coordinates, air mass, seeing conditions. Each image contains thousands of pixels, most recording background sky, a few capturing the comet's faint light, stacked and processed. These images trace the comet's path across the sky, a dotted line moving against the fixed stars, documenting its passage through the inner solar system over the span of months. The light curves exist as tables of numbers, Julian dates, magnitudes, uncertainties, plotted. They show the oscillation of brightness over hours, the pattern repeating with the 7-hour rotation period, the shape evolving as the spin axis precessed and the viewing geometry changed. Buried in these curves is the comet's shape, its surface reflectivity distribution, the locations of active regions, information that can never be fully extracted but that constrains what the nucleus might be. The curves will be analysed and reanalyzed, compared to new models as understanding improves. Mined for insights that were not apparent in the initial observations. Spectra fill other files. Wavelength versus intensity. each spectrum a one-dimensional slice through the electromagnetic rainbow. Emission lines rise above the continuum at the wavelengths of molecular transitions. The CN band at 388 nanometers. The C2 SWAN bands near 470 and 510 nanometers. The OH ultraviolet lines. The strengths of these lines, compared to each other and to the continuum, reveal the gas composition and production rates. The line widths, broadened by the Doppler effect from gas, moving away from the nucleus, hint at the expansion velocity of the coma. Subtle shifts in line positions, if measurable, could reveal rotation of the nucleus or asymmetric outgassing, but the data quality is marginal, the signals weak, the interpretation uncertain. Astrometric measurements form the skeleton of the dataset, right ascension and declination at specific times, measured to fractions of an arcsecond. These positions fit to a dynamical model, yield the orbital elements, semi-major axis, infinite, for a hyperbolic orbit, eccentricity, greater than 1, inclination, longitude of ascending node, argument of perihelion. The elements define the trajectory completely, where the comet came from, where it passed closest to the Sun, where it is going. But the numbers come with uncertainties, expressed as covariance matrices quantifying how errors in one parameter correlate with errors in others. The uncertainties shrink with each new observation, but they never vanish. The orbit is known, but not perfectly. Non-gravitational accelerations are parameterized in the orbit fit. Radial, transverse, and normal components, modeled as functions of distance from the Sun. These parameters capture the effect of outgassing on the trajectory, the tiny rocket thrust that pushed the comet slightly off the path it would have followed under gravity alone. The values are small, measured in meters per second squared or less, but statistically significant. They confirm that the comet was active, that jets were pushing it, that the spin and orbit were coupled through momentum transfer. The parameters are consistent with the observed gas production rates, closing the loop between different types of observations. Derived properties fill summary tables. Estimated nucleus size, 200 to 400 meters. Albedo, around 4%. Rotation period, 7 hours, with uncertainty of minutes. Gas production rates, tens to hundreds of kilograms per second, depending on distance from the Sun. Dust to gas ratio, approximately 0.5 to 1. Each value is an estimate, a best fit result from models applied to incomplete data. The uncertainties are often large, sometimes factors of 2 or more, reflecting the difficulty of measuring small, distant objects, but the values are plausible, consistent with solar system comets, providing a quantitative description of 3Y/8less, even if precise details remain elusive. Papers are written, submitted to journals, peer-reviewed, published. The first announcement paper reports the discovery and initial observations, the interstellar trajectory, the coma detection, the preliminary orbit. Later papers analyze specific aspects, the rotation and precession, the composition and gas production, comparisons to other interstellar objects and solar system comets. Each paper cites earlier papers, building a literature around the comet, a body of knowledge that grows over months and years as more researchers contribute analyses and interpretations. The comet becomes a fixture in the scientific record, a case study in interstellar comet properties, a reference point for future discoveries. The data are archived in public databases, accessible to anyone with an internet connection. The images go to the Mikulski Archive for space telescopes, if observed with Hubble, or to various ground-based archive systems if observed from Earth. The orbital elements are logged in the Minor Planet Center's database, updated as new observations refine the trajectory. Spectra and photometry are published as supplementary materials with the papers, or deposited in data repositories where they can be downloaded and reanalyzed by other researchers. The comet's data outlive the comet's visibility, preserved digitally, available for study long after the comet itself has faded beyond detection. Future surveys, with larger telescopes and more sensitive detectors, might detect the comet again years from now, if they happen to point in the right direction and if the comet has not yet receded too far. But the probability is low. The comet is dim, distant, moving through a region of sky that is not particularly interesting to most surveys. It will likely remain unobserved, its position extrapolated from the last measurements, its fate inferred but not confirmed. The data from this apparition will stand as the only direct observations of 3I/Atlas, a snapshot of a few months in a journey that spans millions of years. Models built from the data will be refined, tested against future interstellar comets as they are discovered. Each new interstellar object provides additional constraints on the population's properties: size distribution, composition, spin rates, activity levels. 3I/Atlas is one data point in that population, its properties contributing to statistical analyses that seek to understand how common interstellar comets are, how they compare to solar system comets, what they reveal about planet formation and ejection processes in other stellar systems. The comet becomes less an individual object and more a representative sample, its uniqueness subsumed into averages and distributions. Only took a few dozen nights of telescope time to gather the data. Only needed months of analysis, countless hours of coding, modelling, fitting, writing to extract what could be learned. Only required the coordinated effort of observers, theorists, data analysts, and journal editors to transform raw photons into published knowledge. The process is routine, repeated for every newly discovered object, but each time it produces something new, a small addition to humanity's understanding of the universe. A single comet story told through numbers and graphs and peer-reviewed text. The comet itself continues, indifferent to the archive, to the papers, to the models and interpretations. It carries no copy of the data, no memory of being observed. It simply moves, spinning its 7-hour rotation, tilted slightly from the spin it had before perihelion, colder now as sunlight weakens, returning to the dormancy that characterized most of its existence. The ice that briefly sublimated is gone, dispersed into the solar wind, atoms now scattered across the inner solar system. What remains is a slightly smaller nucleus, its surface perhaps altered, its spin axis perhaps still precessing faintly, a changed object carrying forward into time. What remains in the data is not the comet, but its ghost, a mathematical description, a set of constraints, a collection of measurements that once corresponded to something real. The data will outlast the observers who gathered it, will outlast the telescopes that captured the photons, will outlast perhaps even the memory of the comet itself as newer discoveries eclipse it. But for now, the data exists, preserved, a whisper of 3I/Atlas encoded in bits and bytes, a message from interstellar space stored on spinning hard drives, waiting for anyone who cares to read it. The comet moves through darkness now, far beyond the orbit of Jupiter, where sunlight is a pale glow. 1/25th the intensity fell to Earth. The ice no longer sublimates. The coma has collapsed. The few remaining gas molecules long since dissipated into vacuum. What remains is the nucleus alone, bare, silent, a dark speck of ice and rock tumbling through space at a speed that will carry it out of the solar system entirely within a few more years. The spin continues, uninterrupted, 7 hours per rotation. A rhythm established millions of years ago and only slightly altered by the brief encounter with warmth. The axis points in a direction tilted from where it pointed before, a lasting mark of the torques that acted when jets pushed against the nucleus. But now there are no jets. No forces act except the faint tug of distant planets, negligible at this range, and the even fainter pull of the galaxy itself, patient and inexorable. No telescope